Why is the speed of light the fastest anything can go in the universe? What Richard Feynman discovered about it will completely blow your mind. Let's unravel this cosmic mystery simply. These effects are not illusions caused by clocks or rulers. They are real changes in how time passes and how space is measured. Now, here's the crucial point. As the object's speed approaches the speed of light, these changes become extreme. Time slows more and more, lengths shrink more and more. The object's motion through space-time tilts closer and closer to the path that light itself follows, but it never crosses it. It cannot cross it because crossing it would require time to stop completely and then reverse, which the structure of space-time does not allow for objects with mass. This is closely connected to energy. To increase the speed of an object, you must give it energy. At low speeds, this works the way you expect. A little energy gives a little increase in speed. But as you get closer to the speed of light, the same amount of energy gives less and less increase in speed. The object becomes harder and harder to accelerate, not because it is pushing back, but because space-time itself is changing the rules. To actually reach the speed of light, you would need an infinite amount of energy. That's not a dramatic statement. It follows directly from the equations. Infinite energy is not something the universe can supply, so the speed of light becomes an absolute limit. Suppose you have a clock on a spaceship, moving very fast. From the point of view of someone inside the ship, the clock works normally. Nothing unusual happens. The seconds tick by as they always have. But someone watching from outside sees something different. The clock on the moving ship runs more slowly. This is not because the clock is broken, or because signals take time to reach us. It's because time itself is passing more slowly for the moving system. This sounds unbelievable, but it's not optional. If time did not behave this way, the speed of light could not be the same for all observers. The slowing of time is exactly what is required to make the laws of physics consistent. The same thing happens with distance. A ruler, placed along the direction of motion of a fast-moving object, appears shorter to an outside observer. Again, nothing happens to the ruler from its own point of view. The atoms don't compress. The material doesn't change, but space itself is measured differently depending on motion. These two effects, time slowing down and length shrinking, work together. They are not separate tricks. They are two sides of the same phenomenon. As something moves faster through space, it must move more slowly through time. There is no way around this. The faster the motion, the stronger the effect. As the speed increases, these changes become more dramatic. Near the speed of light, time almost stops for the moving object. Compared to the outside world, distances in the direction of motion shrink dramatically. The object's path through space-time tilts closer and closer to the path followed by light, but it never crosses it. This is the key point. There is a boundary that motion cannot cross. Light sits exactly on that boundary. Objects with mass must stay on one side of it. They can get closer and closer, but they can never reach it. Reaching it would require time to stop completely for the object, and that simply does not happen for anything with mass. This is not a matter of engineering. It's not about better rockets or better fuel. It's about how space-time is structured. Once time slows and lengths shrink the way they do, the speed limit appears automatically. You don't need to add it as an extra rule. It emerges naturally. Feynman liked this kind of explanation because it removes mystery. Instead of saying, nothing can go faster than light because the equations say so, we can say, Nothing can go faster than light because time and space change in exactly the way needed to prevent it. And that's really the lesson here. As speed increases, nature doesn't push back with a force. It changes the way time passes and the way space is measured. That change alone is enough to make the speed of light an unreachable limit for anything with mass. Now let's look at energy, because this is where people usually think the speed limit comes from. They often hear the phrase mass increases with speed and imagine objects somehow getting heavier and heavier until the universe refuses to move them any faster. That picture isn't quite right, but it points in the right direction. What really happens is this: the faster an object moves, the harder it becomes to change its motion. Not because its material changes, but because of how energy and momentum work in space-time. At low speeds, adding energy increases speed in a simple way. You push something harder, it goes faster. Double the energy, you get more speed. Everything behaves the way common sense expects. That's because, at low speeds, the equations of relativity reduce almost exactly to the old Newtonian ones. But as the speed approaches the speed of light, the relationship between energy and speed changes. You can keep adding energy, but the speed increases less and less. The object responds differently to the push. It resists acceleration more strongly in the direction of motion. This resistance is not friction. Nothing is rubbing against the universe. It's inertia, but inertia that grows as speed increases. The object becomes harder to accelerate, not because it weighs more in the ordinary sense, but because its energy is increasingly tied up in its motion through space-time. Energy and momentum are linked to motion in both space and time. As an object moves faster through space, it has less freedom to move through time. The structure of space-time itself limits how the energy can be rearranged. If you keep adding energy, something interesting happens. Instead of turning entirely into more speed, the extra energy mostly goes into increasing the object's relativistic energy, its resistance to further acceleration. The speed creeps closer to the speed of light, but never reaches it. You can imagine this like pushing a cart up a hill that becomes steeper and steeper. You're still doing work, you're still adding energy, but most of that energy goes into fighting the slope, not into increasing your height very much. The hill doesn't suddenly stop you, it just becomes infinitely steep at the limit. The speed of light is that infinitely steep slope. This is why it's misleading to say that the universe forbids faster than light motion. There's no rule posted on the wall. The universe simply responds to added energy in a way that makes crossing that boundary impossible for objects with mass. Light behaves differently because it doesn't have mass. It doesn't move slowly and then speed up. It is created already moving at the speed of light. It doesn't need to be accelerated to get there. That's why it doesn't face the same resistance. For objects with mass, reaching the speed of light would require an infinite amount of energy. Not a very large amount, an infinite amount. No matter how powerful your engine is, no matter how advanced your technology becomes, you can never supply infinite energy. And this isn't a technical limitation. It's not about fuel efficiency or material science. It's built into the relationship between energy, momentum, space, and time. Feynman liked to emphasize that this is not something nature decided. It's something nature is. Once space-time behaves the way it does, once energy and momentum obey these relationships, the speed limit is unavoidable. So the real reason objects can't reach the speed of light is not that they would break apart, or burn up, or collapse. It's that the universe quietly redirects the energy you add. It lets you keep pushing, but it refuses to give you what you want, that final bit of speed.